Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Steve Wu of Rambus. We're going to talk today about rowhammer. Steve, we've heard a lot about rowhammer as a potential security problem. What is it?
Yeah, rowhammer is a really interesting phenomena, Ed. It's something that happens in memory devices like DRAMs, where when you frequently access a location in memory, you can disturb the data that's nearby, and you can disturb it in a way that you cause the bits to flip and basically lose your data. So it's obviously a big security concern and it's something that the industry's been working on for a while to try and get a handle on and figure out how to fix.
How long has this been around, and is it only at the most recent nodes that it's happening?
Well, it's been around for a while. There have been attempts to fix it in DDR4, for example, and DDR5 also has mechanisms to try and fix this row hammer problem. So it's been known to the industry for, I think it's publicly been talked about for about a decade.
And does it get worse as you start migrating down to potentially HBM and GDDR6?
Yeah, really the thing that matters most is how close the cells are to each other. And so as we get these more dense devices at smaller process geometries, the problem becomes more pronounced. It's a form of neighboring disturb kind of issue where the closer you get to your neighbors, the easier it is to disturb them.
We've also been talking about other ideas where you're really drawing multiple devices off of the same DRAM, things like memory pooling, things like that. Does that become a bigger problem as you start using more devices there?
It does. It's really something that's driven by activity in the DRAM, and in particular, it's activity to particular addresses. So in the case of rowhammer, if you do frequently access a particular location in memory, the neighboring locations are subject to this kind of disturb where their bits can flip. And obviously, if you've got lots more activity going into the memory system, you have a much higher chance of actually causing these bits to flip.
And really, that's where a lot of people have been going with their designs, right? They want higher utilization of all the resources.
Yeah, there's that aspect where utilization is going up because it's just better from an OpEx standpoint, but also just because data sets are getting larger and memory is becoming more critical to performance. The memory system itself is being accessed more frequently just because the applications need it.
Let's take a closer look.
Sure.
Steve, what are we looking at?
Here, I'm going to explain what the rowhammer problem is. So what we're seeing right here are rows of a DRAM array that are part of a DRAM bank. And we've kind of labeled these rows row R and R minus one and R plus one are the nearest neighboring rows to row R. And of course, R plus two and R minus two are the neighboring rows of those neighbors. And so what happens in rowhammer is a traditional row hammer attack happens when I repeatedly activate a row, in this case, row R. We call that the aggressor row. And repeated activations can cause the charge in the neighboring bit cells to leak off and flip. What happens is if those bits lose charge or if charge comes around and populates those cells when it's not supposed to, the bit values will flip. And so this is an example of a traditional attack where the neighboring bit cells of row R are affected. It turns out that we have a mechanism already in DRAMs that can correct this, and that's refresh. So for example, if charge starts to leak off of these cells with the green X's, if you can detect that this is a problem, you just refresh those rows and then the charge gets built back up again. It gets restored. Now, the problem, though, is there's another kind of attack that's been discussed by Google where you take advantage of these refreshes. So if we start hammering row R very frequently, and rows R minus one and R plus one are in danger of losing their charge, you can just refresh them pretty frequently. But those refreshes actually act like hammers on their neighboring rows, R minus two and R plus two. So the fact that you're using these mitigation methods, refreshes to rows R minus one and R plus one, they can cause hammers of their neighbors on rows R minus two and R plus two. So that's what makes this such a difficult problem is that the methods that you have for fixing the original attack actually end up causing an attack. And so this is an example of what's called a half double attack or a victim focused mitigation attack where you're taking advantage of the mitigation operations to cause another attack.
And the more valuable the data here, the bigger the problem, right? I mean, this is one of the reasons that the data centers are so concerned about this.
Absolutely. I mean, one of the things that's really challenging is that row hammer attacks can cause so many bit errors that they can become undetected. And so you can cause a calculation to reach the wrong conclusion. You can cause the wrong instructions to be executed. And a system may never even know because it's the number of errors has overwhelmed the error correction capabilities that are currently in the field.
So basically, what you're doing is fuzzing memory, right?
Yeah, in fact, there's a number of different things that can happen. That you can cause undetected errors, which would be terrible. If those errors can be detected, you can deny service because you may put the machine in a state where it can detect there's a problem, but it can't recover from it. There's other things too, where Google has shown that you can cause a privilege escalation, where you can gain access to areas of memory that you shouldn't be able to gain access to by changing some of the security bits that are associated with different processes. So there's all kinds of really terrible things that can happen from the result of a row hammer attack.
So, Steve, why is this really such a problem in servers?
Well, there's really two reasons. So one is it turns out that the number of activates, let's call it the hammer count, the number of times I need to activate row R to cause bits to flip in its neighboring rows, that's been dropping over time. And again, that's because as we get to smaller process geometries, it's easier to disturb those cells. And so that's one concern, is that the hammer count is falling. The other concern is that it turns out that when a server memory controller issues a reference to a particular address, it turns out that that address maps the same way to each DRAM on a DIMM. And so what happens in this example is you see the memory controller is repeatedly activating row address 0020. And you can see here are two different DRAMs that are part of the group of DRAMs that respond with the data. You can see the controller row address in this first column, and you can see the actual location in the DRAM bank where that address maps. So I made up this mapping, but basically here row addresses 0 and 1 map to the first two rows in the DRAM bank, but controller row addresses 20 and 21 map to the next two. And you can see if I'm just repeatedly activating row address 20, what'll happen is in both of these DRAMs, the second row will repeatedly be activated, and the first and third rows can potentially have their bits flipped. And so the problem here is that I can overwhelm the error correction capability because every DRAM in the system can potentially have bits flip. In fact, in the worst case, every bit can flip in row address 1 and row address 21 because those are the rows that happen to be neighbors of row address 20 in each of the DRAMs. Now, the part that's interesting about this is the mappings that people use in the DRAMs. They're not public. And it turns out that there is one exception here, which is repaired rows. So it turns out that there's always some extra rows that we have in the DRAM, and in case there's faulty rows during manufacturing. And so the DRAMs individually will repair and map an address to a good row if that row happens to be faulty. So keep that in mind because the DRAMs are already doing some amount of remapping that are unique to the DRAMs, but the vast majority of rows keep the same mapping.
Same problem whether you're in GDDR6 or HBM.
That's correct. Yeah. It turns out the problem is at the system level, the problem is a little bit different. At the device level, it's the same problem. At the system level, it gets to be interesting because in servers, we often have extra DRAMs that are used for error correcting capabilities, ECC coding and things like that. But it turns out that those ECC codes can only correct a limited number of errors. And in this particular case, if it's possible to flip every bit at a particular neighboring address, that's just way more bits that can be an error. That'll overwhelm any kind of server ECC that's out there today. And so that's really the fundamental problem. And fundamentally, the issue again is just that every DRAM that's responding to the memory request, like a read, every DRAM maps those addresses in the same way. And so you can potentially have bits that are flipping in every DRAM, and that can overwhelm the ECC capabilities of the system as they're designed today. Now, I mentioned this thing about repaired rows. We wrote a paper, and in that paper, you can actually see how we accommodate repaired rows. But here we're just going over kind of the basics of the idea.
So, from a high level, what exactly are you fixing?
What we're going to do now is we've got methods of ECC, of error correction, that are in the field today. What we really want to do is we want to use those methods. So we want to leverage the error correcting capabilities that are already in the field so we don't have anything new to enable, but we want to fix this problem of having too many bits that potentially can flip. And so our goal is we want to allow a system to keep running even after one successful row hammer attack, even if all the bits in the neighboring victim rows have flipped. And we want to make it so that you have to have at least two successful attacks to irreparably damage the data and cause something bad to go on. So our goal here is fine, if we know this attack can happen, we just want to make it the case that you can still run just fine if one attack has been successful.
Any impact on performance or power if you do this?
Actually, the method that I'm going to go over here, there is no impact on performance and there's no impact on power either. And so let me talk about how we're going to do that. So our solution approach is really to limit the number of bit flips at each victim row address, so that if the controller eventually does try and read data from a victim row address, the maximum number of errors that can happen can actually be corrected with existing ECC methods that are in use today. And it turns out there are some really good ones that are out there. And one of them is called single device data correction, SDDC, ECC. Sometimes it's called chip kill. And that's been around for decades and it's in use today. The other thing that servers do is they do this thing called scrubbing, where they periodically, maybe once to a few times a day, they'll read all the locations in memory and they're looking for errors and they'll try and fix them and write the data back into memory. So they'll kind of repair any errors that have happened. Like I mentioned, there's no performance impact and no power impact to the DRAM accesses. And the other thing that's kind of interesting about this technique is it's compatible with a lot of the other mechanisms that people have proposed either in literature or that we've seen in the DRAM specs for DDR4 and DDR5. So it really allows this technique to just layer on top and provide yet another layer of security on top of what's already there.
We've been hearing all sorts of possibilities like compute in memory, 3D DRAM bit cells. How will this affect any of that, or is it still the same problem no matter what you're doing?
Yeah, it's really the same problem. I think in those cases in particular, it does exacerbate the problem because part of why you're putting the compute in memory is to use that memory more frequently. You're really trying to get the most out of it. And so, again, the more frequent accesses to memory can potentially set off these types of attacks inadvertently. What I'd expect to see is as more processing moves closer and maybe even into the memories, that the problem would get worse.
And so, exactly how do you do this? I mean, what's the solution here?
The key observation is that, I mentioned before that the fundamental problem is every DRAM that's responding to the request from the memory controller, they map the addresses in the same way. So they all have the same victim row addresses. The key observation is I can actually limit the number of bits that flip at any victim row address. I can limit it to a single DRAM if I can guarantee that addresses are never neighbors in more than one DRAM. So I'll get to what I mean by that in a minute. But again, remember that when I have a row that I'm attacking, a row address that I'm attacking, it's the victim row address that's in the immediate neighbors that have bits that flip. But if I can guarantee that those controller addresses that correspond to those neighboring rows are never neighbors in more than one DRAM, then anytime I try and read data from a victim row address, I'll only ever have errors from one DRAM. And so I'll illustrate that here in a second. The thing I want to mention is that asking each DRAM to map addresses differently, remember that with repaired rows, the DRAMs are already doing kind of this unique mapping of whatever rows are broken. They're mapping them to the spare rows uniquely. So I'm not really asking the DRAM to do something dramatically different than what it already does today. We're just asking that for every address, that there be an ability to kind of map it in a different way. So it's an incremental design change, and there's really no performance impact. It's something that happens either at manufacture time or at initialization. There's not something special that has to happen during the normal accessing, reading and writing of the DRAM.
With enough compute power, can you change the map there to the point where you understand where all the pieces are and actually adjust it for your own purposes?
Yeah, what's really interesting about it is this mapping that I'm going to show you. It's just one example of many different kinds of mappings that we can have. From a security standpoint, what we do when we analyze its resistance is we just assume people know what the mapping is. And now, obviously, the memory manufacturers, if they were to implement something like this, they could choose to just keep it secret like they do today. But the resistance of the technique, when we analyzed it, we assumed that people knew the mapping. And still, if they know the mapping, it still takes two successful attacks in order to cause irreparable damage to data, whereas today it only takes one.
And can that be extended now to 20 successful attacks? How do you keep improving? Because obviously the hackers get more sophisticated, the tools get better.
Yeah, what a lot of the focus in the industry has been on is with these defense mechanisms, it's to lower the probability that any attack is successful. So people use tracking methods to try and guarantee that they'll know for sure if an attack is happening and they can stop it. Other people use probabilistic sampling techniques. And so it's kind of like these two things that work hand in hand. There's some design mechanism in the architecture, and then there's some tracking method that it works in conjunction with it to lower the chances that you'll actually need to use the defense mechanism. And so the question you asked about how do you continue to improve this, it's really if you can lower the probability that one attack will be successful, you can imagine it's going to be much, much harder to have two attacks be successful. It's kind of like the square of the probability of one attack being successful. That's really what makes this method powerful, is that if one attack can be made hard to be successful, it's really hard for two to be successful. And then what's interesting about this technique is even if one attack has been successful, there's a way to repair it and you can reset the attack back to square one. I'll show you that in a minute. So this technique of remapping is something we call Rampart. It's an acronym that stands for Row Address Map Permutation and Reassignment Technique. And what we're showing here is a picture of the devices that are accessed on a DIMM module to respond to a memory request. And what you see is that each DRAM is going to map those addresses from the memory controller to different rows inside the DRAM core. So it might be a little easier to look at this diagram here in the middle that's in color. What we're going to do is each DRAM is going to take the address from the memory controller and it's going to do a circular left shift by a different number of bits. And we're going to assign each DRAM an ID. And that capability is actually available today in the DDR5 DRAM design. You can give each DRAM a different identifier. And we're going to use that identifier to say DRAM 0 is going to circularly left shift the address bits by 0 places. So it's the same. And DRAM 1 is going to circularly left shift by 1 bit. And you can see when a controller row address 0 comes in, I don't shift it at all in DRAM 0, so it maps directly to the first row. DRAM address, controller address 1 maps to the second row, 2 to the third row, so on. But what you can see is that for DRAM 1, I take my controller row address and I shift it left circularly by 1 bit. Now 0 doesn't have anything to shift, so it maps again to 0. But row address 8000, when I circularly left shift it by 1 bit, that actually maps to the core row 1. And then address 1 maps to core row 2, and address 8001 maps to core row 3. So you can see there's just a different mapping in each DRAM. And this table kind of on the bottom here shows for more DRAM with a shift of 2 all the way through a shift of 9. You can kind of see how different addresses map. Now, what's interesting is let's say that I hammer I keep activating row address 1. And so in this particular DRAM, row address 1, his neighboring row addresses are 0 and 2. But in this DRAM, if I'm hammering row address 1, I'm going to flip bits in these rows which correspond to controller row addresses 8000 and 8001. Now what's interesting is if I'm successful at hammering controller row address 1, I will cause the bits to flip in different neighboring row addresses in different DRAMs. So I've actually kind of done the thing which I wanted to do, which is, I've actually been able now to limit the number of bits that can flip at any victim row address. So in this particular case, you can see if I decide that I want to read eventually from controller row address 0, The only DRAM that will have errors is this DRAM right here, because that's the only one that had a neighbor. Controller row address 0 was a neighbor of the hammered row. In this particular DRAM, row address 0 ended up in a row that was not neighbors with the row that got hammered in DRAM 1. It's
You,
kind of the key is that this mapping, this very simple example of a mapping, there's others, but this very simple example of this mapping is what limited the number of bits that could flip at any victim row address. Now, if the controller eventually reads from controller row address 8000, then in this DRAM, I can have bits that are flipped, but in DRAM 0, those bits are not flipped. So again, I've confined the number of DRAMs to one that have had bit flips from a successful row hammer attack.
you've taken a very persistent problem in semiconductors and you've turned it into a fairly simple math solution here, right?
That's right. Yeah, it's a very simple observation about what a simple type of remapping like a circular shift can do. Again, there are others, and I don't want to make it sound like this is the only way, but the key here is that you want some mapping function that allows neighboring addresses in one DRAM to never be neighboring addresses in others. So you have to have some kind of function that allows, in this case, 10 different mappings for that to be true, because there's 10 different DRAMs involved in providing the memory for the requested address.
Going back a little bit here, Steve, you mentioned that it really takes two attacks to damage the data. Why?
Yeah, so we see here that one successful attack can actually cause bits to flip, but we're limiting the number of bits that can flip, and we're limiting it to one DRAM. And what we're going to do is we're going to leverage some existing ECC techniques that are already out there. So we've talked about how we confined now the bits that flip to a single DRAM. It turns out one of these methods that I mentioned earlier for error correction called chip kill or SDDC ECC, what it does that's really neat is it allows all the bits from one DRAM to be in error. For example, the DRAM can die, or you can have a catastrophic kind of error in the DRAM that causes all the bits to flip. And that's okay. There's enough redundancy among these 10 DRAMs that one entire DRAM's data can be completely invalid, and there's enough redundancy to reconstruct what the data should have been. And so we're going to use that capability here. If one attack has been successful, and it manages to flip a large number of bits, even up to all the bits coming from one DRAM, that's very much like a chip kill situation where a chip has died. And that technique for correcting the bits and coming up with the correct data that should have been coming from that DRAM, that's been in the field for the last couple of decades. So it's already deployed, and we're going to just leverage that capability. So anytime one attack has been successful, the standard chip kill capability takes over and fixes it. Now, the other thing that's interesting that we can do is you don't necessarily need to even know that an attack has been successful, right? So if one attack has been successful and you don't know it, if you read a victim row address, again, only one DRAM will see errors. And so chip kill or SDDC ECC will correct it. I now need a second attack that flips bits in the same victim row address, but in a different DRAM. I need a second attack to be successful. And it turns out that it takes time for these attacks to be successful. Some of these methods are tracking or probabilistic detection. They can really kind of increase the time it takes for one attack to be successful. Well, it turns out that servers do this thing that I mentioned before called scrubbing. They have this thing called patrol scrub, where once to a few times a day, the entire contents of memory is read. And if there are any errors that are in the data, those errors can be corrected as long as they're small enough, a number of errors. They can be corrected, and then the correct data is written back to memory to clear those errors. Well, you can see what we're doing here is if one row hammer attack has been successful, it will flip bits in one DRAM and one DRAM only at any victim row address. Well, when I go through and I read the entire contents of memory, I'm going to hit that victim row address and I'm going to see, hey, there's bits that have flipped at that address. The chip kill ECC will correct those bits and then write the correct values back into memory. And what it does is it basically heals the memory system from that one successful attack, and it causes an attacker to start over again from the beginning. So again, using two methods that are already in use today, chip kill or SDDC ECC and patrol scrub, you can now protect a system that has had one successful attack, and you can undo the effects and cause the attack to start over again. So that's kind of what's really interesting about this technique is just a simple modification of the address remapping that's already done in a DRAM, along with techniques that are already in use today, can provide this higher level of resistance.
What you're talking about here is interesting because one of the big changes that we've seen as we start moving forward is that you can't really, particularly with heterogeneous integration and all the complexity in a system, you can't stop every attack. What you can do is recover from them. And that's really where you're headed with this, right?
Yeah, I mean, obviously we would like it to be able to stop every kind of attack, but in these types of things that are related to security, attackers get smarter. There's new kinds of attacks that come up all the time. And what we're really trying to do here is we're focusing on something that addresses the fundamental issue, which is disturbance of neighboring cells. And we're showing a way that, okay, if something does happen, maybe a future attack comes up, as long as you can recover from one, it makes it harder to irreparably damage the data because it takes two attacks to be successful.
Steve Wu, as always, thanks for a great explanation.
Thanks very much, Ed.